Alright, optimization. Optimization will form quite a big bit of the exam. It is essentially problem solving with calculus. The questions are widely varied and always incorporate some other area of maths, which can be quite a bit of fun, but it's also nerve-wracking because the best way to practice them is to do lots of them. So in a second I've printed out a 45-page booklet that I'll give you of past exam questions. The answers are on Canvas for it, and 3G, where these questions are, I made an hour-long video last year going through some of the answers to 3G. Yeah, these are fun, and they are quite challenging, and it's one of those practice makes perfect things. What you really need to know is quite little in terms of content. Optimization often involves finding a minimum or maximum, and methods will accept two tests to show a minimum or maximum. The first test is the one that we use more often. You can show that you found a maximum by showing a sign diagram of the first derivative. Max, min. That's the one we've used before, and that's frankly the one I would continue using. In theory, there is a second test. The second test is the second derivative. The second derivative test is if the first derivative is equal to 0 and the second derivative is negative, meaning it's concave down and flat, it means you found a maximum. Or you can think of this as concave up and flat. But this is not as good because it involves you finding not just the first derivative equal to 0, but then differentiating again and finding a sign there. So you're having to do two derivatives here, whereas the sign diagram test you just do one derivative. So this is a slightly better one. Rather than go out a textbook, I thought we were doing a couple of past exam questions. We might just have time for one. These exam questions are basically, you need to just understand what they're asking and they lead you through a bit of a story. Each has multiple entry points, meaning if you screw up early, they let you back into the question with show that bits later on. And that's true for most good SAT questions and exam questions. Point P moves along the graph f of x, where f of x is 4 on x, where x is greater than 0. The graphs below show P in 3 different positions. So basically, there's this point P that can slide along this curve. And what they've done is they've shown that as point P slides along, it sets up a triangle. A triangle with the origin and Q. The triangle has a right angle at Q. Let OQ be x units long. So if I were you guys, as soon as they write something that isn't labelled on there, I would label it on there. So let OQ be x units long, I would be getting your pen and labelling a little x here. Because that's what it means when it says OQ is x units long. And then it says OP is L units long. Again, they told you something that's not on the diagram, so just finish the labelling. If OP is L units long, there. Cool. Show that L squared equals x squared plus 16 on x squared. Any sort of feelers of where that's probably come from? Yeah, it's feeling Pythaggy. Alright, really what's happening here is you've got a function that is L, x, f of x. The height of that is f of x high. Yeah? Because when you put in x into the equation, you get out a height of f of x. And if we're after show that, I would say a squared plus b squared equals c squared from Pythag, and therefore x squared plus f of x squared is L squared. X squared plus 16 on x squared equals L squared. Now note, if you didn't get that or don't know where it's come from, it doesn't actually matter, they've given it to you. It's one of those show that's. So if you screwed it up, that's fine, let's just use it and move on. Find the position of P at which L squared is minimized. So remember, P was this movement here, and they're not asking you to minimize L, they're asking you to minimize L squared, which is slightly odd, but what they're doing is asking you to find the minimum of this side of the function. Yeah? So if we're asked to find the minimum of this side of the function, we need to differentiate it, find where the first derivative is 0, show that it's a minimum. And that's the steps after. So we're looking for when we want to minimize x squared plus 16 on x squared. So we need to find, it sounds weird, but L squared dash. They wouldn't care too much about the notation, but we're going to differentiate this. If this is L squared dash is going to be 2x minus 32 on x cubed. Got that one right? Feels good. Then we set it equal to 0 because we want to find the maximum. So I'm going to set it equal to 0 and I'm going to bring this whole thing over. 32 on x cubed equals 2x. I'm then going to multiply both sides by x squared. No, I'm going to multiply both sides by x to the 3 and divide by 2. Happy there? Then take the 4th root of 16, which just works out nicely. X equals plus or minus the 4th root of 16 will be 2. But because x is greater than 0, x is just equal to 2. And because they've said the word minimized or maximized, you need to show that it's a minimum or a maximum. There's only one solution here, but you would still need to include a sign diagram of f dash x against x, and you want a 2, and I wouldn't put an arrow there, I would put a 0 because we stop at 0, and you know it's a minimum. They've told you it's a minimum. If you want to, you can substitute into the equation, but frankly we're just going to cheat a little bit. It's going to be minus plus because that will give it a minimum. Therefore, L squared is minimized when x is 2.
And then you plug the 2 back in to find the y coordinate?
I think we just want p. Oh yes, you're right. Should find the position of p. Yeah, so if we plug in 2 to the equation, what was it? X on 4?
X squared plus 16 and x squared. Oh.
No, yeah, 4 and x.
Oh, yeah.
So then this height here would be 2, 2. Yeah, so the position of P is 2, 2. Nice? Alright. Then, because they like adding a little spice, they'll often pull different areas of maths together. Show that when L squared is minimized, OP is normal to Fx. Alright. In order for things to be normal, would you be happy that the slope of OP, if I multiplied it by the derivative or the slope of the function, they'll get minus 1? Because that's the sort of test for being perpendicular, is when you multiply them together, the slopes together, they become minus 1. So what they're really asking you to show here is that the slope of OP multiplied by f dash 2 is equal to minus 1. So the slope of OP multiplied by the derivative of the function at 2 where they meet should be minus 1, and that will prove it's normal. How do we get the slope of OP? I mean, if we've got the position of P, and we definitely have the position of O because it's the origin, yeah, rise over run. So between the origin and the point 2, 2, what's the slope of OP? 1. Yeah, that's 1 times f dash 2. Now f dash was, well, f is 4 on x, right? Therefore, f dash 2 is going to be minus 4 on 2 squared. Because if we're going to differentiate this, the minus one will come out the front and become a minus 2. This would be minus 4 on 4 is minus 1. Which is kind of what we're after. The slope of OP is 1. The slope of the function at that point is minus 1. They multiply together to make minus 1.
Why do you want it to be minus 1 originally?
Because we wanted to show they're normal, so meeting at right angles. If we multiply the slope of OP and the slope of the function, and they equal minus 1, it means they would meet at right angles. And that would be enough to show they're normal.
Okay.
If it said they were parallel, we'd want to show the slopes are equal, for example. But yeah. We don't have time to do the next. There is another question here. The answers are on Canvas. And then, basically tonight, keep going with 3F, make a start on 3G, and then we have our lesson tomorrow, and I'll give you them as well. And then next week we'll start kinematics. And we'll continue all of this tomorrow. Don't leave without those booklets.